Okay, so we continue with the lecture 38 of the series. In the last class, in the last lecture, I mentioned about some of the basic stability criteria dealing with waves. We are continuing here with the same, we are continuing here on the same topic of waves and some effects on stability due to waves, or some changes in the stability of the ship due to waves. So, the main thing we have seen is due to the presence of there are two cases, as we have seen in the last class. There can be a case of a sagging wave or the case of a hogging wave. Now, these two represent a case when a sagging wave represents the case of a trough existing at the ship's midship, or the midship of the ship is really riding on a trough, that is called as a sagging wave condition. And when the midship of the vessel is riding on a crest, we call it as the hogging wave condition. So, in these two conditions, we have seen that the stability of the wave can be enhanced or decreased as a result of the change in GM, and the change in GM occurs because of the shift in the metacenter or the position of the metacenter, and this occurs because of a change in the breadth of the vessel. So, when the effective breadth of the vessel, rather, there is no change, not much of a change in the breadth of the vessel at the center ship, that is midship, where you have a more or less wall sided ship formula, wall sided ship. So, you see that the breadth of the ship is more or less constant with draft, but when you go towards the aft of the ship or to the forward or the front part of the ship, the bow of the ship, you see that the breadth is very much dependent upon the draft. So, as the draft keeps increasing, the breadth of the ship keeps increasing, and as a consequence of this, you see that when the draft is higher in the forward side, which means that it is a sagging wave condition. If it is in the trough, therefore, the breadth is more, M is higher, GM is more, and therefore, the stability is more. When the ship is riding on a crest, the stability is less. So, GM now becomes a function of time. So, this whole problem of response of the or the movement of the ship in the wave or the movement of the ship in the sea, that is whether we are talking about the different degrees of, we will see what are the different degrees of freedom now. Before that, we know that we can represent any, we have already done this, we have seen that the response of the ship, the heeling of the ship, the heel angle can always be represented by a simple formula, phi double dot plus therefore, we have seen that the heeling of the ship or the heeling response of the ship can always be represented by this. This is a very simple formula of simple harmonic motion, where you have the angular acceleration phi double dot directly proportional to minus of, or directly proportional to minus of the displacement, that is heel phi in this case, and therefore, and here GM is the metacentric height, I is known as the radius of gyration, we know that, and G is the the acceleration due to gravity. So, G by I square into, now what does this problem become in the case of a what does this problem become in the case of a ship that is now on a wave crest. So, that is now riding on a wave. So, as we have seen, the ship finally ends up with a wave. It finally, in most of the seas, the ship ends up being in a wave condition, which will be in which the waves will come in the direction of ship, what we call a 0 degree angle, and we call it as following waves. The ship can the waves can come 180 degrees to the ship, the direction which we call as head waves. So, when any of these waves come, the waves will then propagate across the ship, or not across, propagate along the ship. So, when it propagates along the ship will alternately be on a wave crest, a trough, a crest like that, and its GM varies with time. Now, if you write the same equation, the simple harmonic motion, we can modify it in the presence of a time varying GM. Now, as we have seen, we have here heel acceleration is now proportional to it is equal to a constant times the heel angle, and this constant is now GM, something into GM. So, if GM now becomes a constant, a variable with respect to time, this equation can be written as okay. So, what this equation shows is that the equation that this is now a GM0, which is a constant, which is the presence of, that is in the absence of waves. So, it is GM in the absence of waves plus delta GM. Now, this delta GM is a function of time. Okay. This is the important point. Delta GM is a function of time, that is the GM, it is the perturbative part of the GM. So, the GM, the net metacentric height, is now a sum of a stable component, which is a fixed component, which is basically for a still water line, and it is, and on that it is superimposed a perturbative component of GM, which varies with time, which is actually a function of the wave. The position of the wave or the location of the wave and the position of the ship on the wave decides whether the decides what the GM is, and consequently what this delta GM is. So, we get this as the new equation. This becomes our final equation, and now what we can very simply do is, remember the wave, it is a wave. So, it's varying with time in a periodic fashion. So, one possibility, the simplest way of dealing with this problem is if you assume that the variation of GM is sinusoidal. It is of course not probably true, but we can always assume it to be correct. It is some delta GM, some value into cos omega t, omega e t, let us call it, into phi equal to 0. Now, therefore, what have we done here? We have just assumed that the variation of GM with time, that is, as the ship is going over the wave, now there is a wave like this, and as the ship is going over the wave like this, it is going in a, the GM is varying in a cosine fashion, it is varying in a sinusoidal fashion, in a cosine fashion, and once you assume this, you get this equation, and this equation is known as the Mathieu equation. It is slightly important, it is known as the Mathieu equation. Now, this is the equation that is mostly used to solve the response of ship in seas. Now, let us write the first of all, suppose that you have an equation like this. The main equation that we started with is, suppose it is something like this, x double dot plus h. Suppose there is a mathematical equation of this form, that is, you have x, which is the horizontal position of the some particle, varies like this. It is a kind of simple simple harmonic motion, but note that this h is a function of time. So, it is not purely simple harmonic. Now, this is a differential equation, and this kind of equation is known as a Hill's equation. So, this equation where the coefficient, the coefficient of the differential equation is a function of time, is known as the Hill's equation, and in the particular case, if we are able to write h of t as a delta plus epsilon of t, no, epsilon is also a constant, and yes, you write it as epsilon of t, which is equal to delta plus epsilon cos omega e t. Now, suppose you are able to write it like this, then this equation is called as a Mathieu equation. This is the equation that we just mentioned. This is the equation that represents a this is the equation that represents a this is the equation that represents the ship's motion or the heel of the ship on the wave. So, if you have a wave propagating and you have a ship on it, and then the equation of the motion of the ship, the equation of motion of the ship is given that heel motion, phi is always the heel, phi, the heel motion is always given by the Mathieu's equation. in this, the important point to note is there are two components, there are two constants, one is delta and the other is epsilon, and what you see is that this delta in Mathieu's equation applied to ships. Note, Mathieu's equation was not generally defined for ships as such. He is a mathematician, he was a mathematician, and it was applied for just mathematical problems, and it is now going, this equation is now applied for ships as such, that is all. So, this is Mathieu's equation applied to ship motion, the differential equation applied to ship motion, and in the case of ship motion, the Mathieu equation will have the following constant. This delta will be equal to gm and epsilon will be delta gmt. So, what you can understand is, right from looking at it, this delta represents a stable component, the natural component. Gm natural means gm is a property of the ship. Now, actually gm is a property of the ship and it is a property that can be modified as a result of probably a wave. So, if you have a wave, it can modify gm. There are other properties also that can modify gm, external properties that can modify gm. Now, but in general gm is a property of the ship, and that natural gm is what we call as gm 0, the natural gm not subjected to the wave, and that gm 0 is the natural, it is a property of the ship, it is the natural component of the gm, and that is given as delta here. This delta represents that gm 0, it is a constant, it is a natural, and epsilon here represents the delta gm, which is a perturbation, means which is a fluctuation about the still value. So, if you have gm 0 to be the still or the mean value of gm, the fixed value of gm on a still water line, then epsilon is a perturbation over it, and therefore, epsilon represents the if you want to call it the perturbation or the exciting component or the fluctuation acting on delta. So, epsilon is a perturbation acting on delta, which is the mean, and cos is the this is how it varies. Epsilon is a value and cos, this is the direct, this is the this is the way in which it varies. In a sinusoidal fashion it varies. Now, so therefore, we have the equation like this. Phi double dot plus this delta plus epsilon into phi equal to 0. So, this equation comes as a result of the Mathieu's, this is the Mathieu's equation for ships. Again, delta is the natural component and epsilon is a perturbative component, and this is a sinusoidal variation of the perturbation. Now, once you have this equation, any differential equation, it can either have stable solutions or unstable solutions. What do we mean by a stable solution? Suppose you have phi, I mean suppose you have this equation, that is phi double dot plus something, and suppose you solve the equation and you get an equation, you get an expression for phi as such, which is means you get an expression for phi, whatever it be, it could be in the, like you know that it depends upon the type of the real and imaginary part, that is depending on the type of equation, the differential equation, it can, you might end up with a solution that is like a cos something, or it might be an e power something. So, these are general differential equations, these are the two kinds of solutions you end up with, you get either a cos function or a e power function. Now, suppose you end up with a function that is bounded. By bounded we mean it does not increase exponentially, or it does not increase, just does not keep increasing, mostly exponentially, when then such solutions are called as bounded solutions, and those solutions which increase without a limit, or it increases in an exponential fashion. So, once that is phi, when it is a function of some parameter, when phi suddenly increases without any limit, then such, if the variation of phi is in that fashion, then you call that, you say that phi is unbounded. So, the solutions of phi which are bounded, we call it as stable solutions. Solutions of phi which are unbounded, which increase in an exponential fashion, very rapid increase, we call it as unbounded solutions. So, you have the bound solutions and the unbound solutions, and which are the which represent the stable and the unstable regime, depends on it's the that's what phi depends on. So, if you draw the variation of delta with, so for such a, for a ship case, this is for a ship's case, if you draw the variation of delta with, means if I draw delta here and I draw epsilon here, note one represents gm, the other represents delta gm. If I draw a case like this, you will see that so when you draw the curve between delta and epsilon and you see the values of delta and epsilon, and correspondingly you will have values solutions for phi. Now, you will see that some regions of delta and epsilon will give stable solutions, whereas some regions will give unstable solutions. So, these regions where I have shaded are represents the regions of stable solutions, and the regions where it is unshaded, like here, it represents unstable solutions. So, what you see is that you have different types of, you have the different solutions to this Mathieu equation, and you end up with two regions of delta and phi, delta and epsilon. You end up with some regions which are a region of stable solution and some regions which are region of unstable solution. Therefore, you see that most of the solutions occur when delta is equal to, means this bifurcation region occurs when delta equal to 1, then it occurs when delta equal to 2, then it occurs when delta equal to 4, like that. These are roughly the regions where these bifurcations come. So, this is one point that is to be noted. So, these diagrams which draw the variation between delta and epsilon are known as Strutt-Innes diagrams. It will be helpful to remember this name. This is known as the Strutt-Innes diagrams. These are diagrams which represent the regions of stable and unstable solutions for this Mathieu's equation. Now, similarly, consider this equation. This is the same equation. I have just changed it from phi to x, that is all. Suppose you have the equation, it does not obviously in this case represent a heel, it represents some form of translatory motion. It could be surge sway, but we will come to what is surge sway and all that, but it represents some form of translatory motion. Now, let us suppose that we make the assumption omega t is equal to 2 T1. We define like this, we define some non-dimensional T1 such that omega t is equal to 2 T1. Therefore, we see that x dot can be written as dx by dt, dt1 by dt. Now, what is dt1 by dt? You get it here, omega by 2. So, it is equal to omega by 2 into dx by dt1. Similarly, x double dot becomes dx dot by dt1 by dt, which again becomes omega square by 4 d square x by dt1 squared. So, this is x, we are just changing the equation into now, if you substitute these two in this equation, okay, if you put it there, you will end up with x double dot plus delta 1 plus epsilon 1 cos 2 T1 into x equal to 0, where x double dot is equal to d square x by dt1 square, x, and it's just been transformed from one system of coordinates to another system of coordinates, from t to t1 it has been shifted. And similarly, you will get a, if you were here, delta 1 will represent 4 sigma squared by omega squared, epsilon 1 equals 4 epsilon by omega square, and this is just from this simple manipulation you will get these two values. Now, what you see here is, here look at this equation. What do we mean by the first of all, we have the case of a undisturbed solution, okay, and we can have a case of undisturbed solution. Undisturbed means when the perturbation component is 0, it will be like saying that is the case when you have your, there is no wave. That will be the case in the ship. In this case, it will be a case where there is no wave. So, if you put this to 0, you get x double dot plus sigma square x equal to 0, your omega will become sigma by 2 pi. This is known as the natural frequency of oscillation of the ship, or natural frequency of the ship. Okay, this is the natural frequency of the ship. This we have already given an expression. Remember, we have given some class back, we have given an expression for the natural frequency of the ship. Natural heel frequency, there are different frequencies, there can be pitch, there can be heel, there can be yaw, different kinds of things, but we are talking about the natural frequency of heel for a ship. It depends upon gm, it depends upon I, that is the radius of gyration, and so some root of I by gm, something like that, it comes to an expression of for omega. So, this is actually sigma by 2 pi, where sigma in this case becomes gm, and not gm, gm by I square or something. If you just check back, you will see that. So, omega is equal to sigma by 2 pi. So, this is known as the natural frequency, and then there is a frequency of the perturbation itself. It is this. Now, we have this epsilon cos omega t. So, I just want you to know what are the two types of frequencies we talk about here. One is the natural frequency of heel. If this in this case, this does not represent the heel motion, it is x double dot. So, it is not heel motion, this represents the natural frequency of whatever translatory motion we are discussing here, the natural frequency of that motion of the ship, natural frequency, and this epsilon cos omega t represents the perturbative oscillation of the ship, and epsilon is a perturbative value, and omega here we can call it omega e, it is the perturbative frequency. Now, therefore, we have, so we ended up with solution which said that delta 1 is equal to 4 sigma squared by omega square. Here we have seen what is sigma, and this omega is the perturbative frequency, epsilon 1 is 4 epsilon by omega square, again these are all perturbative frequency. Then you will similarly have a strut-ins diagram can also be drawn for the delta 1 epsilon 1. Remember, all we have done in the delta 1 epsilon 1 is we have converted from a t domain, that is the time domain, into another non-dimensional t1 domain. It's almost the same thing, we are still talking about, it is just easier to, it is just a domain which makes it easier to do some calculations, that is all, but it is basically the same Mathieu's equation. So, we have similarly a strut-ins diagram for the, this is also known as a strut-ins diagram only. So, you will have at 0, 1, similarly you will have drawings like this. I believe it becomes here. So, what you see is that like this, you have similar drawings. So, some regions which are shaded, some regions which are not shaded. So, these unshaded regions represent the regions of unstable, unshaded or unstable, and shaded regions represent stable regions. So, these are two types of these are two regions in this strut-ins diagram which represents the stable and unstable regions. Now, you see that the if you draw the diagram properly, I am not drawing it once more. So, when you draw the diagram properly, you will see that when delta 1 equals 1 square, 2 square, 3 square. So, in these regions, okay, in these regions close to 1, 4, 9, etc., you come at one point like this, where you have here an unstable region, like I will take for example 2 square at 4 in the Struttin's diagram. This is delta 1. In the Struttin's diagram, there will be like this epsilon 1. At when you reach, when delta 1 becomes 4, this is a region of unstable. So, here it will be shaded. So, here it is stable, here also it is stable. So, at this points you reach a region where the where there is a boundary between the unstable and the stable region, or rather we can say that these are points of these values of delta 1 are regions where the solution becomes unstable. So, it changes from stable to unstable, or these are the dangerous regions in the ship, where delta 1 equals all these values are the dangerous regions of the ship, and that is these represents or 1, 2 square etc., represent the dangerous areas of the ship. Let us take the first solution equals 1, it is dangerous. Therefore, what do we see? We see that when the perturbative oscillation is twice the natural frequency of oscillation, remember sigma was the natural frequency of oscillation, and when the perturbative frequency omega becomes equal to twice the natural frequency of oscillation of the ship for that particular kind of motion, whether it is heel or pitch or roll or whatever it is. So, when omega is equal to 2 sigma in this case, you come to one of the unstable solutions of the ship, unstable dangerous situations of the ship. So, when omega equals 2 sigma, there is an unstable or there is a dangerous condition. Now, next when omega equals, or next case when 4 sigma square is equal to 4 omega square, or when omega equals sigma, this is another dangerous case. Now, so like this. So, this is some kind of resonance, we call it parametric resonance. You know that resonance is a condition when the frequency of vibration or oscillation of the perturbating force or the perturbating whatever is causing the perturbation exciting force, if the frequency of oscillation of the exciting or the force that is generating the noise or vibration is equal to the natural frequency of oscillation of the system itself, of whether in this case a ship. So, if the frequency of oscillation of the perturbation is the same, is twice the angular frequency of natural frequency of oscillation of the ship, then you have a parametric resonance occurring, and this produces a very dangerous condition. So, the ship can means phi can go in an unbounded region, and you know that when you say that phi goes unbounded, the meaning is that the phi can increase, means if this is phi, if phi keeps increasing, it means that the ship will capsize. So, it is a dangerous situation. That's so these are different. This phenomenon is known as parametric resonance, and it is a interaction between the perturbating. Remember, the perturbating force here is the wave. So, the perturbating frequency or the frequency which is causing the excitation on the ship in this case is the wave. So, when there is a relation between the wave frequency and the natural frequency of oscillation of the ship, let us consider heel. If the natural frequency of oscillation of the heel and the frequency of the ship has a relation, if they are equal, or if they are related in such a fashion, if they are in some ratio, then you will end up with parametric resonance, a region when there is very high vibration and very high phi can go, phi becomes unstable or it goes into a capsizing mode. So, these are different types of parametric resonance that you come across in ships. Then there is another term which we talk about, we call it as the frequency of encounter. this is a term that is used commonly, is known as the frequency of encounter. It means actually it is a kind of relative motion between the ship and the coming wave. So, if let us assume that a wave is, again as I told, let us assume that a wave is coming directly onto the ship, we call that as a head wave. So, when a wave comes and hits the wave directly, the ship goes over the wave, and let us suppose that we are measuring the time taken between the means the time period or the time elapsed between two successive position, means that suppose that the ship is measuring two successive positions of the crest. So, it measures one crest coming, then it waits, it undergoes some oscillations, and then it sees the next crest coming there. So, the time between elapsed between these two positions of the crest reaching there. So, this is some time period is elapsed between the two. So, that time period is called as the time period of encounter, and the frequency associated with it is 2 pi by T e, which is the T e is the encounter time period. So, 2 pi by that T e will give you the encounter frequency. Now, we will see what the method is. Now, we have again I am going to assume some basics of waves. When I say basics of wave, it is the absolute basics of waves, that we are not talking about even slightly engineering concepts, like we are not, I am not assuming that you know even things like the dispersion relation, because there is a bit of wave that we will cover in the next lecture, very little bit, that is a little bit of its engineering application, which is it is actually the beginning of wave studies, wave theory, and but right now at least things like wave, crest, trough, the wave time period, frequency, then the what we call as, there is also wave speed, such things will be known to you, we assume that it is known to you. So, let us assume that the speed of the wave, we also call it as a wave celerity, which is the speed with which the waves propagate, or let us assume that the crest of a wave propagates. So, that is c, and let us assume that the ship is moving at an angle alpha like this. So, there is a ship here and there is a wave coming c. It can be either way, means you, if it can either be coming like this or the wave is coming like this, either way this wave is coming, the ship is there, and this is a very simple case. Now, let us assume a case when the ship is like this, means it is at an angle to the wave, this is the wave, it is at an angle, the ship is propagating with a velocity v. So, the ship is now moving with a velocity v at an angle alpha relative to the wave. So, c, that is v. Now, we can see that the relative velocity between the two is c minus v cos alpha, okay. So, or c plus v cos alpha, depending upon the sign of c, whether the ship is, whether the wave is a following wave or a head wave, depending upon that we will write it as c minus v cos alpha or c plus v cos alpha. At any rate, it will be v cos alpha. Now, we can say that how much time is, now how much time does it take for the wave? Okay, first of all, let us see this way, how much, what did we say? We said that the time period between the seeing of two wave crests. Now, if you see two wave crests, that means you have traveled a distance of lambda, that is a wavelength. So, to see two wave crests, you must have traveled a distance of lambda, and the time it takes, and right now we have seen that the relative velocity with which the ship is moving is c minus v cos, or the wave is c minus v cos alpha. So, the distance moved is lambda and the relative velocity is c minus v cos alpha. So, the time taken to move that distance, or which is also the time taken to see two successive wave crests, is equal to, the time period is lambda by c minus v cos alpha. Okay. This is straightforward. So, this is what we call as the encounter time period. This is known as the encounter time period. This is the time period between two successive encounters of a wave by a ship. So, if you take the frequency of this, which we call as omega 2 pi by T of this T e, this becomes anyway you just put it there, C minus V cos alpha by lambda into 2 pi. So, this will give you the value of the encounter frequency. This is what we call as encounter frequency. Then this is now we can always get a relation between the you can always get a relation between the frequency of the wave itself and the frequency of the frequency of the wave and the frequency of the encounter frequency. You know that the frequency of a wave can in general be written as C by lambda sorry lambda by C. So, is it C? The frequency is given by no sorry C by lambda, sorry this is. So, you can get the omega of the wave, that is the angular frequency of the wave, by C by lambda, and the angular frequency of encounter by this expression C minus V cos alpha by lambda into 2 pi. Now, so from these two expressions we will get values for we will get the relationship between the frequency of the wave and the encounter frequency. Okay, then this is some basics of parametric resonance. Now, we will also before we wind up the course, we will also discuss some details about waves, some basic formulations of waves, some concepts of wave theory, some very basics of wave theory. Now, in wave theory, first of all, a few assumptions are always made. The first assumption of which is that the wave is the fluid is incompressible. The meaning of the fluid is incompressible is that the density of the fluid does not change. Okay, so the density of the fluid does not change with time. And what do we mean by incompressible or compressible? There are some cases very rarely found in oceans as such, but more found in atmosphere, cases when you end up with the air when you change up with a very large change in the density of the fluid, whether it be the air or the water. When you encounter a sudden drastic change in the density, this can happen. It mainly happens when you, for instance, if you have a aircraft instead of a ship, and when you are studying aircraft, suppose that those are you know that when the speed of the aircraft gets up to the speed of sound, when it equals the speed of sound, which is something like 350 meter per second in air, we say that the aircraft has reached a Mach 1 speed, and when any velocity greater than that, we call it as supersonic velocities, and Mach 1 plus is all supersonic. In fact, I believe some of the fighter jets go at even beyond the Mach 2, which is twice the speed of sound. So, at any rate, when you have the aircraft traveling at speeds greater than the speed of sound, when you reach a situation where density is highly variable in supersonic flows and transonic flows, you end up with flows which end up with a situation where the density of the fluid changes very rapidly. So, that is a case that such a case does not arise in the ocean in ships, because ships go at very slow speeds. So, that is one possibility. When you have drastic changes when you have sudden changes in the temperature or possibility in the atmosphere, the moisture content of the atmosphere, or in the case of ocean, the salinity of the ocean. So, either of these, I mean, if you are studying air and airplanes, then you see that when your moisture or temperature changes very rapidly, your density can change. so the air becomes compressible in that sense. There is a dou rho by dou T, there is a compressible compressibility effect. Then, and in the other case, in the ocean, if you have a change in temperature or a change in the salinity, you will have a change in density as well. The change in temperature is such that if you have an increase in temperature, the density decreases. If you have an increase in salinity, the density increases. Salinity, by the way, is defined as a salt content of the ocean. So, if the salt content increases, the density increases. So, these possibilities, removing all these possibilities, in a simple case, we say that fluid is incompressible. That is how wave theories are developed. All the cases are for the case when the fluid is incompressible. That is number 1. Number 2, we are assuming that the fluid is inviscid. Now, the meaning of the term inviscid is that the fluid has no viscosity. Now, viscosity is a concept in fluid mechanics which might not be familiar. Viscosity is a property of all kinds of fluids, whether it be gases or liquids. So, water also has a viscosity. So, viscosity, because of the viscosity property of water, there is acting always on the fluid a force called a viscous force. It is like a frictional force. So, when you have a body traveling through the water or an air, for example, if you have a plane traveling in the air or if you have a ship traveling in the water, this viscosity will act on this viscous force is a kind of force that will act on the ship or the plane and prevent it from moving. So, it is a kind of drag produced, and this drag is called as a viscous drag. And another effect is that and another effect of viscosity is the generation of heat. So, because of viscosity, there is a generation of heat and dissipation of heat. So, production of drag and dissipation as heat, these are two properties of viscous fluids. Now, we assume that there is no such thing as viscosity and that the fluid is absolutely inviscid. So, that is the next assumption. Then we assume that again in fluid mechanics there is a term that is known as rotational property or rotation of the fluid. So, we say that if the fluid is, you either say a fluid is rotational or a fluid is irrotational. A more detailed analysis or more detailed discussion of rotation and irrotation is beyond the scope of this lecture. So, it is not appropriate for this hydrostatic instability, but we say that a fluid is irrotational. The meaning is that it has zero vorticity. A property of fluid exists called vorticity, which is the rotational property of a fluid and fluid parcel, and therefore, in this waves we assume that the fluid is irrotational. So, now we are always talking of small amplitudes. The amplitude by amplitude of a wave we mean this, means if you have a wave like this, its fluctuation or its displacement away from the mean, this is what we call as amplitude. Now, what we are assuming is that this amplitude, this distance is much smaller than this distance. This is known as a wavelength, as you know, lambda. So, we say that the amplitude of the wave is much smaller than the wavelength of the wave. So, this brings us to a small amplitude wave theory, and this is the simplest form of wave theories. And of course, there are theories which do not make this assumption, but in general here we are going to deal with this. And so, we have small amplitude waves. Then the main equations which we come across in the wave theory are, first one is we use the equation of continuity. The equation of continuity is written as, let us consider a two-dimensional flow where you have, we are not considering the transverse motion of the ship or a transverse direction of the ship. Therefore, we have only the x and the z direction. So, you have only the longitudinal direction of the ship and the vertical direction of the ship. it is just a simplification. I mean, it's not, we are not saying that that is the case, but it does not make a big difference whether you consider the because it is a small, first of all the main properties which we want to study occur in the longitudinal direction, that is what we are mostly interested in. So, and depth is needed definitely to come because of the weight criterion. So, dou u by dou x plus dou w by dou z equal to 0 is what we call, this equation is what we call as the equation of continuity. This equation states that it is basically a restatement of the basic principle of mass conservation. We say that the mass of a fluid is never means a mass is never destroyed as such. Water as it is always remains as water. So, it is not going anywhere. So, whatever mass of water is there, it is there even after, whatever is there before is there after also. So, this concept comes as dou u by dou x. Derivation, none of these we are going to any derivation. So, dou u by dou x plus dou w by dou z equal to 0 becomes the continuity equation, and in the case of a in this case of analysis of waves, which is usually done what is known as a potential method. We call the study is known as the potential flow methods or potential flow theory. Why is it called a potential flow theory? Because we deal with the potentials, we deal with the we will deal with what is known as a potential. I will tell you what is potential. We say that u is equal to a dou phi by dou x and w is equal to a dou phi by dou z. We make a definition like this. So, what we say as phi is known as a velocity potential. We define it as a velocity potential phi. So, this phi is what we call as a velocity potential, and therefore, what is the simplest formula that comes from what the two equations that I wrote before, that is u is equal to dou phi by dou x and w is equal to dou phi by dou z, can be combined together in a way as u vector is equal to actually del phi. So, it can be written like this, and when you combine it with the now, so this equation of for phi these two equations when combined with the equation, the continuity equation, this is the continuity equation, you put this value for u here, you will see that the equation reduces to this in vectorial notations, or the on this notation of del can be written as del square phi is equal to 0. Now, this equation is known as a Laplace equation and is the basic equation for waves. This is the equation from which this is the equation that describes a wave. So, we say that when a fluid particle obeys Laplace equation, there are some basic assumptions that go as you have seen already. First of which is that potential exists. The meaning of potential exists is that vorticity is 0. So, again these are allied concepts, but the concept is you get the idea of Laplace equation. Then so, this is the equation of a wave. So, a wave follows this equation del square phi is equal to 0, where phi is the potential velocity potential. So, phi is the velocity potential, and now this equation of Laplace equation is now solved subject to some boundary conditions, because you cannot get a solution for phi unless you have some boundary conditions. You have some conditions which say what is the value of phi at some point. So, we have some we can put some constraint. First of all, remember a wave is like this. Let us consider the free surface of liquids. So, there a wave is like this. Okay. Therefore, there if you have a wave like this on the free surface of let us say ocean, for instance, if you have the free surface like this. Now, if you say that this is psi, which is the displacement of the free surface, what we call as elevation. Psi at any point represents the shape of this curve. So, here psi is positive, here psi is negative. At any rate, the variation of psi represents the position of this curve. So, position of psi represents the position of this curve at any point. Now, this psi, therefore, what is called as elevation represents the shape of the curve. Psi of x will mean this curve, actually this curve, usually which we write as f of x, the function of x is written as this psi of x, that is a curve. Now, what is at this curve, what is the movement of, what is the velocity of the curve in the, what is the variation of this curve. Now, as you can see, this curve is in the z direction, okay, this psi is in the z direction. Therefore, if you want to get the vertical velocity of the particle, the movement of this is a psi, and this psi is a function of time. So, because of various factors acting on the surface, this psi varies with time. And how do we get its variation with respect to time? This is got by so just think of it, it is the variation of displacement with time, it gives the velocity. So, it gives elevation is a vertical displacement, and variation with time represents, it actually represents the velocity, vertical velocity of this curve. So, this curve, what is the rate at which it is moving in the various, it is the rate at which it is changing, it is a vertical direction, and how it is varying like this. At any instant, psi at any instant of x is actually psi is a function of x and time, not just time, psi is a function of x and time, and this psi, how it varies with time, it will be varying like this at some x. If you fix the x, psi will vary like this. Now, you can see it is a variation in the w direction or the z direction. Now, this is the variation of the curve. Now, what can you know about the particle that is residing inside that curve? You will see that a particle will be moving up and down with the curve. It is a wave, wave is made up of this particle only. So, when this wave goes up and down, the particle also goes up and down, and what is the velocity of the fluid particle? The vertical velocity of the fluid particle is dou phi by dou z. Okay. This gives the vertical velocity, we have already seen that w is given by dou phi by dou z. This gives the vertical velocity of the fluid particle. Dou phi by dou z is equal to w, and at z equal to 0, we will see that dou psi by dou t is equal to dou phi by dou z at z equal to 0. Now, that is what we have eventually said here is that the rate of movement of the curve, rate of fluctuation of the curve is equal to the rate of, it is equal to the water particle velocity. There is water particle inside that curve. So, the rate at which the curve moves is equal to the water particle velocity, the rate at which the water particle also oscillates or moves up and down. So, that therefore, this expression holds at z equal to 0 and is known as the kinematic free surface boundary condition. It is known as the kinematic boundary condition. So, this is a free surface condition, kinematic free surface. So, this is known as a kinematic free surface boundary condition, that is one of the conditions on which the wave theory holds. So, since the time is up today, we will stop here now and we will continue in the next lecture. Okay, thank you.